Hi everyone, this is my first video in solid state chemistry classes. See, in solid state crystallography, in order to understand the characteristic properties of crystals, we have three important laws. One is called law of constancy in interfacial angles, that what we also called as Steno's law. Number two, we have law of rational indices that we also called as Hayes law. And thirdly, and most importantly, the law which is proposed under crystallography is law of crystal symmetry. So before going to the core of the law of crystal symmetry, we should know what is the exact meaning of the term symmetry. Symmetry in the sense, when you rotate a crystal about a particular reference point after a complete revolution, say for a 360-degree rotation. After 360-degree rotation, if the crystal exhibits the same appearance, then the crystal is said to be showing symmetry. That is the simple meaning of the term symmetry. And if you come to the case of crystal symmetry, law of crystal symmetry, each and every crystal will show various types of symmetries. And according to law of crystal symmetry, all the crystals of the same substance will possess the same elements of symmetry. And here I used a word called as elements of symmetry. And what is elements of symmetry? Just now I said each crystal will possess various types of symmetries, and all the different symmetries exhibiting by a crystal is simply called as elements of symmetry. And there are three important elements of symmetry called as center of symmetry, which is also called as point of inversion, or you can also call it as point of symmetry. Secondly, it is plane of symmetry, and thirdly, it is axis of symmetry, which is also called as line of symmetry. So totally we have 7 crystal systems. Each and every crystal do exhibit elements of symmetry. But in current context, let me consider only the cubic crystal for explaining all these 3 elements of symmetries. And at the end of this video, let me conclude the different numbers of planes and axes of symmetries exhibiting by the remaining crystal systems other than cubic crystals. And now we shall enter directly into the details of each and every element of symmetry. First, we shall go with center of symmetry. So according to center of symmetry, if you consider a crystal, and within that crystal, if you consider a simple imaginary point, a point which is present within the crystal, and through that point, if you draw a line joining either the opposite faces or the opposite corners, whatever it may be, when you join the two opposite faces or opposite corners by drawing a line, and that line is drawing or passing through that imaginary point which is present within the crystal, provided if from that point, if the crystal surfaces or the crystal points, that is corners, meets at exactly same distances, exactly at equal distances in both the directions, then the crystal is said to be having center of symmetry, and that imaginary point is considered as center of symmetry or point of symmetry or point of inversion in that particular crystal system. Let us see that how the center of symmetry will will be in a crystal system. So here is one cubic crystal wherein there is a one imaginary point that is here, and through that imaginary point the lines have been drawn to the opposite faces, wherein from the point the faces meeting at same distances, you can see in the picture. And in this you can see the center of inversion. This is the point wherein the opposite corners have been joined through by drawing a line, and from that point the two corners will be present at the same distance. So it is also the center of symmetry or center of inversion. Now, the second element of symmetry is plane of symmetry. If you consider a crystal, and through that crystal, if you pass a plane either through the opposite faces or through the opposite edges, if that plane cuts the crystal into two equal halves, provided if one part is exactly the mirror image of the other part, then the crystal is said to exhibit plane of symmetry. And the condition for the plane of symmetry is a thing when a plane is passing through the crystal, there were two parts what we are going to get, they are supposed to be exactly mirror images to each other. If not, means though the plane is cutting the crystal into two parts, if they are not exactly mirror images to each other, then the molecule or the crystal cannot be said to show plane of symmetry. So the plane should divide the crystal into two parts and one part is exactly mirror images to the other part. That is a condition for a crystal to exhibit plane of symmetry. So the simplest definition for plane of symmetry is if an imaginary plane can divide a crystal into two parts such that one part is the exact mirror image of the other, then the crystal is said to have plane of symmetry. And as I said, a plane can be passed either through opposite faces or through opposite edges. So depending on how the plane is cutting the crystal into two halves, there are two kinds of planes of symmetries are possible. One is called as rectangular plane of symmetry. Rectangular plane of symmetry. And number two is diagonal plane of symmetry. So there are two planes of symmetries. One is rectangular plane of symmetry and other one is diagonal plane of symmetry. And now we shall see what is the exact meaning of rectangular plane of symmetry. See, a rectangular plane of symmetry is one. So this is the plane in case this is a rectangular plane of symmetry in which the plane is passing through opposite faces. The plane is passing through opposite faces in case of rectangular plane of symmetry. And in case of diagonal plane of symmetry, so here the plane is passing through diagonally opposite edges. And that's the differentiation between rectangular plane of symmetry and diagonal plane of symmetry. And let us consider the rectangular plane of symmetry. As I said, if the plane is passing through opposite faces, then we used to call that as rectangular plane of symmetry. And we know that in case of a cubic crystal, totally we are having 6 faces. So 6 faces divided by 2, totally 3 rectangular planes of symmetries are possible in case of cubic crystal. So as I told you in the previous element, that is there is one center of symmetry in each crystal system. So we already said in cubic crystal there is one center of symmetry, and here there are 3 rectangular planes of symmetries because totally we have 6 faces. One plane will cover 2 faces, so 6 divided by 2, totally we are having 3 rectangular planes of symmetry in cubic crystal, and that we shall see how the 3 rectangular planes of symmetries are there in this cubic crystal. Here you can see the planes are passing through opposite faces, and that cuts the crystal into 2 halves where each part is exactly mirror images to each other. So having the plane of symmetry. And now if we come to diagonal plane of symmetry, as I said, the plane is passing through opposite edges. And we know that in cubic crystal there are a total of 12 edges, right? So 12 divided by 2, there will be 6 diagonal planes of symmetries are possible in case of cubic crystal. So as a whole, we will be having 3 rectangular planes of symmetries and 6 diagonal planes of symmetries. As a total, there are 9 planes of symmetries are present in a cubic crystal. And now we shall see how these 6 diagonal planes of symmetries are there in a cubic crystal. Here are the 6 diagonal planes of symmetries. You can see in the crystal, the plane is passing through diagonally opposite edges, so that dividing the crystal into 2 halves. Again, the one part is exactly mirror images to other part, so that here also the condition is satisfying, that is the plane of symmetry which cuts the crystal into 2 halves, wherein each part is exactly mirror image to other part. Now we shall go to the third element of symmetry, that is axis of symmetry, which is also called as line of symmetry, and in majority of cases this will be called as alternating axis of symmetry also. And according to this, when you are rotating a crystal about a line which is passing either through opposite faces or through diagonally opposite corners or through diagonally opposite edges, whatever it may be, when you are rotating the crystal about that axis to a certain angle, if after complete revolution, that means after giving rotation of 360 degree, if the crystal exhibits same or similar appearance, then the crystal is said to have axis of symmetry, and the line about which we are rotated the crystal will be called as axis of symmetry or line of symmetry. That means the crystal will be rotated by keeping the reference of that line about a certain angle. Say for example 90 degree. If you are giving 90 degree rotation for one time, so this will be the arrangement of the crystal. After giving one rotation, the appearance what the crystal show will be similar to that of original appearance. And after one more rotation, so again one more similar appearance. So totally we gave 180 degree rotation. So now one more rotation 270 and one more rotation that completes 360 degree rotation. So the appearance what the crystal shows after fourth rotation, that is giving after 360 degree rotation, will be similar to that of original structure. But when you gave 90, 180 and 270 degree rotation, the appearances of the crystal will be similar to that of the original, but not exactly the same, but they are similar. So such a kind of axis about which we are rotating the crystal for certain angle and for the certain numbers of rotations, after a complete revolution, if the appearance of the crystal is exactly the same as that of its original appearance, then we used to say the line as axis of symmetry or line of symmetry. And just now I said we can rotate the crystal for certain angle. So depending upon to what angle we are rotating the crystal, and after certain number of rotations we are getting the original appearance, the axis of symmetries are of more number of types. So now we shall learn the different types of axis of symmetries. So in that, the first one is fourfold axis of symmetry. Or this fourfold axis of symmetry is also called as tetrad axis. Fourfold axis of symmetry or tetrad axis. The name itself telling you, that means we are giving 4 rotations, and this will comes into picture if the line, if the axis is passing through opposite faces. So when the axis of symmetry is passing through opposite faces, that axis will gives that axis will be a fourfold axis. That means if you are rotating the crystal about that axis, after 4 number of rotation, after 4th rotation, the crystal will give same appearance as that of its original appearance. Okay, so here the complete revolution is 360 degree. So number of rotations we are giving is 4. So 360 degree by 4 is 90 degree, right? So that means for each time we are giving a rotation of 90 degree. And as I said, the fourfold axis of symmetry is the one, the fourfold axis is one which is passing through opposite faces. And in a cube, we are having a total of 6 faces, right? So one axis covers 2 opposite faces. So 6 divided by 2, there will be total of 3 fourfold axis of symmetries are present in cubic crystal. And now we shall see one of such fourfold axis of symmetry that is present in a cubic crystal. Here you can see the axis or line is passing through opposite faces. So when you rotate the crystal about this axis, after 4th rotation, the crystal exhibit the the same appearance. So hence it is calling us fourfold axis of symmetry. And there are totally 3 such fourfold axis of symmetries are there in a cubic crystal. And number 2 is threefold axis of symmetry. This threefold axis of symmetry is also called as triad axis. So since the fourfold axis is the one in which the line is passing through opposite faces, right? And here the threefold axis is the one, or it is the axis is passing through a threefold axis is the one which is passing through diagonally opposite corners. Okay, when the line is passing through diagonally opposite corners, and that will give a threefold axis in case of cubic lattice. And now we shall see to what angle we have to rotate the crystal in order to say it is threefold axis. So now the complete revolution is 360 degree. How many number of times we are giving the rotations? 3 times. So 360 degree divided by 3, that gives 120 degree. So for each time we have to rotate the crystal for 120 degree. And here in case of fourfold axis of symmetry, when you are giving first, second and third rotation, the appearances are similar to the original, and the appearance what you will get after fourth rotation will be the same appearance as that of original. And here in case of threefold axis, when you are giving first and second rotations, the appearance what crystal shows will be similar to that of original, and the appearance what you will get after third rotation will be the same as that of its original. Okay, so here I said when the axis is passing through diagonally opposite corners, we will be getting a threefold axis. And now we shall see how many such threefold axis of symmetries are present in a cubic crystal. So here we said corners, and we know that in a cubic crystal there are a total of 8 corners are there, right? So there are 8 corners, and each axis will cover 2 opposite corners. So 8 divided by 2. So as a total, we are having 4 threefold axis of symmetries in a cubic crystal. And now we shall see one such threefold axis of symmetry which is present in cubic crystal. And here is the threefold axis of symmetry. You can see the line is passing through diagonally opposite corners. When you rotate the crystal about this axis, after a third rotation, the crystal exhibit the same appearance as that of its original structure. Therefore, in cubic crystal, since there are 8 corners, so as a total, there are 4 threefold axis of symmetries are possible in cubic crystal. And thirdly, twofold axis of symmetry. Twofold axis of symmetry, which also called as dyad axis. Twofold or dyad axis. So that means here the axis about which we are rotating the crystal need to give two rotations in order to get the same appearance for the crystal as that of its original. That means the appearance before giving the rotations. So when we used to get such a twofold axis of symmetry, right? So if the axis is passing through, if the axis is passing through again diagonally opposite edges, then that gives a twofold axis. So here the complete revolution is 360 degree. So we are giving two rotations in order to get the same appearance. So for each time we have to give a rotation for 180 degree. So for first rotation the appearance will be similar to that of original, and after second rotation it completes the 360 degree revolution and the appearance of the crystal will be same to that of its original. So in case of a cubic crystal, since a twofold axis is one which is passing through opposite edges, and in a cubic crystal we are having a total of 12 edges. So each axis covers 2 edges. So 12 by 2 we will be having 6 twofold axis of symmetries. So as a total, we are having 6 twofold axis of symmetries, 4 threefold axis of symmetries, and 2 fourfold axis of symmetries. So as a total, we'll be having 3 plus 4 plus 6, 13 axis of symmetries are present in a cubic crystal. And now we shall see one twofold axis of symmetry that is possible in a cubic crystal type. And this is the one twofold axis of symmetry. You can observe the axis is passing through diagonally opposite edges. When you rotate the crystal about this axis for an angle of 180 degree for one rotation, after second rotation the crystal exhibits the same appearance as that of its original appearance. Since there are 12 edges in a cubic crystal, so as a total we will be having 6 twofold axis of symmetries. So as a total, we said in cubic crystal there is one center of symmetry, and there are 3 plus 6, totally 9 planes of symmetries are there, and now 6 plus 4 plus 3, 13 axis of symmetries are there in a cubic crystal. So as a total, with 13 axis of symmetries, 9 planes of symmetry, and 1 center of symmetry, one cubic crystal do exhibit 23 elements of symmetry. There are a total of 23 elements of symmetry in case of cubic crystal type. So this 23 crystal elements of symmetry covers 1 center of symmetry, 9 plane of symmetry, and 13 axis of symmetry. So total 23 elements of symmetries are there in a cubic crystal. And now we shall see the number of planes of symmetries, number of axis of symmetries, and number of center of symmetry. Not number of center of symmetry. I said while discussing the center of symmetry, each and every crystal system will have only one and only a center of symmetry. There may be a different number of planes and axis of symmetries, but there will be only one center of symmetry is possible. And now we shall see the number of planes and axes of symmetries that are present in the remaining crystal systems other than cubic. So we know that there are 7 crystal systems: cubic, tetragonal, orthorhombic, monoclinic, triclinic, orthorhombic and rhombohedral. So about cubic crystal, we have given the complete discussion and we said there are a total of 23 elements of symmetries, and now we shall see how many elements of symmetries are there in the remaining crystal systems. So in order to remember the number of planes and number of axes of symmetries that are present in a particular crystal system, shall go with one simple mnemonic. And this concept is much more helpful in getting marks in competitive examinations like JAM, GATE, as well as in CSIR NAT examinations. And now we shall see the number of axes and number of planes of symmetries that are present in each and every type of crystal systems other than cubic. Okay, and now we shall look over into the different number of elements of symmetries that are present in the crystal systems. So for that, in order to remember the number of elements of symmetries, let us go with one simple mnemonic. That is, you just remember this: Raja of Malwa took triplex house. Okay, so Raja is a very worthy person, right? So he have the capability to purchase a triplex house. So 1, 2, 3, 4, 5, 6. So totally 7 crystal systems. About cubic crystal we already discussed, and now we shall see about the remaining 6 crystal systems. R refers to rhombohedral, O refers to orthorhombic, M refers to monoclinic, T refers to tetragonal, and here you can observe I have given as a tri, that accounts for triclinic, and H refers to hexagonal. And now we shall see how many elements of symmetries are present in each of this. That is rhombohedral, orthorhombic, monoclinic, tetragonal, triclinic, and hexagonal. So these are the 6 crystal systems, and now we shall see how many plane of symmetries are there, and how many axis of symmetries are there, and number of center of symmetry. So obviously there will be one center of symmetry in each case. And now we shall see how many planes and axis of symmetries are present in these remaining crystal systems. So just in order to remember this, just go with this way. So hexa, that means 6, right? So just you rise with one number, go with the 7, and here you write the 7. Okay, and 7 in triclinic there is no plane of symmetries, and it is looking like how much? Minus, right? So 7 minus, here it is, here we did hexa, so increased by one number 7, and here it is tetra, you increased by one number, once again that is 5. So how much? 7, it is looking at minus, 7 minus 5 is how much? 2. Mono means 1. So here we don't have any sign, so add it. So 7 minus 5 is 2 plus 1, it is 3. So whatever the numbers you got over here, replicate the same in case of axis of symmetries also. 7, 3, 1, 5, minus, and again 7. So in this way, you can remember the number of planes and number of axis of symmetries present in the crystal systems rhombohedral to hexagonal. So as a whole, in case of rhombohedral, 7 2s are 14 plus 1, 15 elements of symmetries are there. And in case of orthorhombic, 3 2s are 6 plus 1, 7 elements of symmetries are there. In case of monoclinic, there are a total of 3 elements of symmetries, and in case of tetragonal there are 11 elements of symmetries, and in case of triclinic, which is the most asymmetric crystal system having only center of symmetry, and in case of hexagonal 7 to the 14 plus 1, again 15 elements of symmetries are there. And that's about the elements of symmetries that are present in crystal systems. So in this video we learned about the meaning of each and every element of symmetry, that is center, plane and axis of symmetries, and we have given one mnemonic in order to remember the number of axis and planes of symmetries present in a particular crystal system. If you feel the video is worthy and informative, please like it, share it, and do subscribe the channel and press the bell icon so that you will get the notification for any update in the channel. Thank you.